Hi everyone, I am here to present our work Testing Product Distributions, a Closer Look. This is a joint work with Arnab Bhattacharyya, Saravanan Kandasamy, and N.V. Vinodchandran. I'll start by introducing the problem of hypothesis testing in high dimensions. In this problem, we are given samples from two unknown distributions P and Q over the Boolean hypercube, and our goal is to distinguish between the following two cases. P is close to Q with respect to some distance function d1 such that d1 between P and Q is at most epsilon by 3 versus P is far from Q with respect to some other distance function d2 such that d2 between P and Q is at least epsilon, where epsilon is an input parameter between 0 and 1. We would need the condition d2 is at most d1 so that in the closeness case we have also d2 between P and Q is at most epsilon by 3 so that no pair of distributions P and Q satisfy closeness and hardness condition at the same time. We'll be referring to this problem as d1 versus d2 testing, and our algorithm is supposed to succeed with 2/3 probability, which can be improved to any number close to 1 using independent repetitions. And we'll be interested to perform this task with respect to a minimal number of samples that we'll be referring to as the sample complexity of the problem. Now, the high dimensional setup comes with certain natural hardness results. First of them is the statistical hardness, which says that this d1 versus d2 testing problem for certain choices of d1 and d2 would require something like 2 to the n samples in the worst case. Then we firstly note that computationally, since the sample space size is 2 to the n, an exact distance computation would take so many time. And then there are hardness results which says for distributions coming out of Boolean circuits, this problem of d1 versus d2 testing for certain choices of d1 and d2 is complete for certain classes beyond polynomial time. So in order to evade the previous hardness results, we'll be making certain statistical assumptions about P and Q that they come from certain nice classes of distribution. For this talk throughout, we'll be assuming that both P and Q are product distributions, meaning each of the components are independent of the other. And then we have also some results about Bayesian networks. And there are other models such as Ising models, which we do not look at in this work. And for every case, we hope to get polynomial in n and epsilon sample and time complexity. So we'll be looking at 4 distance function in this talk. First of them is the total variation distance, which is the half of the L1 norm between P and Q. Second is the squared Hellinger distance. H square PQ is defined as the half of the L2 norm between half of the squared L2 norm between the distributions square root between the vector square root of P and square root of Q, and Hellinger distance between them is defined as the square root of the Hellinger squared distance. The Kullback-Leibler divergence KL distance between P and Q is defined to be summation over I, Pi log the ratio of Pi and Qi, and is used heavily in information theory. Finally, we'll also look at the chi-square distance defined as the summation over the items in the sample space I, Pi minus Qi whole square divided by Pi. And for these 4 distance functions, we have an important inequality here that we'll be referring to again and again, which is that TV is at most some factor of Hellinger distance, at most square root of KL, at most square root of chi-square. As we said, D2 is at most D1, we need this condition for well-definedness. So we'll be choosing a pair of distance functions D1 and D2 from these 4, and we'll be looking at the problem of D1 versus D2 testing. There are certain variants of this problem. Firstly, we look at the tolerant versus non-tolerant testing. So what I have defined so far, D1 versus D2 testing, is actually known as the tolerant testing. Then there is an easier case which in the nearness case requires us only to distinguish P equal to Q from the D2 between P and Q is at least epsilon, which is easier than the tolerant testing. Then we also have a variance identity versus closeness testing. In the identity testing problem, P is assumed to be unknown, but Q is completely specified. In the closeness testing, P and Q are both unknown and sampleable. So if we make a matrix out of these 4 choices, we'll see that the identity and non-tolerant problem is the easiest of the 4, and the closeness and tolerant problem is the hardest of the 4. So in this work, we make a table choosing distance function D1 and D2, which will be represented in the columns and rows for any particular problem, say any particular item in this matrix. Let's say this chi-square versus TV, will be interested in the sample complexity upper bound, how many samples we take in order to solve this problem. We'll be also looking at the lower bound, how many samples are needed in order to solve this problem. And due to this inequality I just mentioned before, the problem becomes harder as we travel these entries from left to right and also from top to bottom. So we'll be making two such table, one for identity testing and a similar table we'll also make for closeness testing. Here I have omitted the columns for KL and chi-square because it is known that the simple problem of non-tolerant testing becomes harder for these distance function KL and chi-square, and it is not possible to solve this problem in any finite number of samples. So first of all, we'll look at the previous work when Q is known. That's the identity testing case. For this problem, the non-tolerant testing with respect to total variation distance was known to be solvable in square root of n epsilon to the minus 2 samples, and that many samples were needed, also known to be needed in the worst case. For the TV versus TV problem, it was known that n by log n samples are needed, and there was an algorithm which could solve it in n epsilon to the minus 2 samples for the Boolean case, and it would also work when P and Q are product distributions over the hypercube sigma to the n, when each of the components come from the alphabet sigma. Similarly, for the Q unknown case, there were a known result for the non-tolerant testing case with respect to total variation distance, and the previous two results I mentioned about the TV versus TV, those two results are exactly the same for the Q unknown case. In particular, we can observe that the tolerance behavior was not looked at thoroughly with respect to alternative distance functions, and also previous works were mostly limited to the Boolean alphabet size, and the non-Boolean alphabet was not easy to extend. Our motivation for these shortcomings of previous work and our focus on those comes from the following theoretical and practical perspective. Firstly, in property testing, the total variation distance is usually considered, but the other three distance functions I mentioned are as important in statistics and machine learning. So in a previous work, 2018, Daskalakis et al. Studied alternative distance functions for the univariate case. Our goal in this work is to study alternative distance function in high dimensions. In practice, data generation process is often modeled as a multivariate distribution, such as bioinformatics machine learning. And in such settings, the distribution is inherently high dimensional and involves features which are Boolean, which are not Boolean. And tolerance is also a demand in those cases where the Q need not match exactly P, the unknown distribution P, but could be only close to the distribution Q. I now come to our results. First of all, we show that the problem of non-tolerant testing with respect to total variation distance needs at least square root of n times sigma epsilon to the minus 2. This strictly extends the previous lower bound, which did not involve any alphabet size. For the upper bound, we show that the harder problem of chi-square versus Hellinger, that could be solved in the tight sample complexity square root of n times sigma epsilon to the minus 2. And then we extend the previous work of TV versus TV, which was shown to take n by log n many samples. We show that even the testing square root of KL versus TV would take so many samples. Finally, we also show a new upper bound for the Hellinger versus Hellinger problem, which would take n size of the alphabet epsilon to the minus 2. Similarly, for the Q unknown case, we extend the previous result for the non-Boolean alphabet case for the non-tolerant testing with respect to total variation, and we also show a upper bound for the Hellinger case. And here, interestingly, we show that even the problem of chi-square versus TV becomes n by log n samples it is needed in the worst case, which for the identity testing problem could be solved in square root of n sample complexity, but the square root of KL would take so many samples for the identity testing. So that's an interesting result. And then we also have the Hellinger versus Hellinger testing problem we could solve in n times alphabet size epsilon to the minus 2. In particular, I want to mention that all the upper bounds are time efficient and all our upper bounds involve the non-Boolean alphabet. I'll just conclude with a few insights from our work. Firstly, for the chi-square versus Hellinger case, we leverage on certain important inequalities that if I look at the distribution P, whose ith component is Pi, and I look at the Q, whose ith component is Qi, and I traverse this inequality from left to right, then we observe that for the Hellinger squared distance, the distance function is sub-additive in terms of the component distributions. For the KL distances, it is exactly additive, and for the chi-square distance, it is super additive. So using these three facts, we show that it suffices to test whether the summation of chi-square distance component-wise is small or large, which we achieve through a known tester. And ours is also the first lower bound that involved alphabet size for the identity testing problem without any tolerance, where we extend the previous work involving the alphabet size. For this, we map each of the component distribution pi over sigma to a distribution f of pi over the hypercube 0, 1 to the size of sigma. Let's say pi is the distribution pi1, pi2 up to pi sigma. Then we map to the distribution f of pi, which is Bernoulli pi1 times Bernoulli pi2 times Bernoulli pi sigma, which is over the alphabet size 0, 1 to the sigma. Once we have that, effectively we get a Boolean alphabet distribution, which is n times size of sigma dimensional. And then we build upon the earlier construction to get our square root of n times sigma epsilon to the -2 lower bound. That's all I have for this talk. Thanks for attending.